more fun with Newton's method for finding roots. So just remember the idea behind Newton's method is we have some function and it has some roots. So let's suppose we have a function that looks like this here. And we need to calculate one of its roots like this one right here. Newton's method relies on a tangent line approximation that we just repeat. And there's a pretty easy way to repeat that in a recursive process. So we might not know this exact number, but we zoom in and we pick a number nearby, and then a tangent line projects us closer than we were before, and we get this new x value, and that tangent line projects us closer, and we just kind of zoom in there on it. Now, Newton's method can fail if we don't use it right, and it can fail just because there's a lot of weird things that happen in math. If I had a bad guess about the root, like maybe I guessed at an x value over here, then that projection of the tangent line could throw me over to this root instead. So we do have to be pretty selective about how we pick our first guess in Newton's method. The algebra behind it is pretty straightforward. It's basically find the tangent line and then solve for x to get the next value. When we do that, our new x value always has the same appearance. It's going to be equal to the previous one. I'm just going to call it x1 for now, our first guess, minus the function value evaluated at that guess divided by the derivative evaluated at that guess. And we just repeat this process over and over. So this is what we call a recursive process. And so the question of how does a computer find or estimate these roots? This is one technique of doing so, and humans keep developing new and faster techniques. And so there's a whole bunch of other ones. So although this maybe 20 years ago would have been a common routine for finding roots on a calculator, the code in the background that found the root for you, these days we have slightly faster ones. And there are math courses just designed in those kinds of algorithms if you ever go into further math about this stuff. So we're going to take a look at the function f of x equals x squared minus 12, similar to the one we did yesterday. If we look for roots of this sucker right here, right, we set it equal to 0, we get x squared equals 12, x equals plus or minus the square root of 12. So there's two possible roots we could find using Newton's method. We're going to go plus or minus for the positive square root of 12 in this case. And we're going to start with a bad guess just for fun and see what happens. And then we'll go from there. So to apply Newton's method, we need to know the derivative. So let's write that down. And sometimes cleaning these up algebraically can help. Sometimes the algebra doesn't really go anywhere, but it's usually worth a shot. So here's our function, x squared minus 12. Our derivative, f prime of x, would simply be just 2x. And so then Newton's method says new x values come from taking some previous x value, plugging into the function, so that would just be x squared minus 12 divided by the derivative, which would just be 2x. And that should be an x1 there and there as the previous guess. Now we can clean this up a little bit, so I'm going to do that just for fun. We would need a common denominator here, so we'd multiply top and bottom by 2x1. And so then I get 2x1 squared. And then here, careful, distribute the minus x squared plus 12 all over 2x1. Cleans up a little bit more, so we get x1 squared plus 12 over 2x1. And I'm going to stop there. It turns out we can take it another step, and I'll show you that in just a minute. So then we make a guess. So we're trying to find the square root of 12 here as our goal. And let's say somebody makes a bad guess by saying, well, half of 12 is 6, so let's try 6 as our first guess. Now that's a pretty bad guess, but let's just do it anyway. So if we go with that, right, that's my x1. Sometimes we call it an x0 for the first guess. I'm going to call it x1. So then my next guess will be based on that. I just use my formula up here. I'm going to square that number, add it to 12, and divide by twice that number. All right, so let's do that. That gives us 36 plus 12, 48, divided by 2 times 12. Let's see, did I do that right? 36, 48, 2 times 12 is 24. That does not look right. Do I have an error here? X minus f of x over f prime of x. That's definitely f prime of x. No, that looks right. I was just not expecting to get 2 as the next one. All right, let's see what happens. So then we just keep plugging in. So then my third one, repeat the process, 2 squared plus 12 over 2 times 2 is going to give me, what, 4 plus 12 is 16, divided by 4 is 4. Yeah, this works out okay. And then x4, and usually I'm going to automate this in a calculator or on a spreadsheet. I'll show you a couple ways to do that in a sec. 4 squared plus 12 over 2 times 4. 16 plus 12 is what? 28 divided by 8, which is what? 4 goes into 28 7 times 2, so that gives me 3.5. And then we're going to start getting decimal values, which is pretty typical. So I'm just going to whip out a calculator to automate this a little bit more. And I think I will use Geogebra today. So one cool thing I'll show you I like about Geogebra for this. So my formula, again, is given a particular number. So I'm just going to say A is my first number equals, where was I at? 2.5, 3.5, 3.5. I can then just keep repeating this. Now I'm going to set it up as a function. So let's say n for Newton's method of x is equal to x squared plus 12. Oops, I need my fraction. Ah, oh boy. Divided by 2x. Let's get that plus 12 in there. Okay, so there's my Newton's method. I really don't want to see the graph of it. That's not relevant because we're hitting this recursively. So then I can just say, okay, what is n of A? And it gives me the next value there. And the nice thing is it automatically called it B. And so now I can say, okay, what's n of B? And it gives me this number. It's going to call it C. And I can say, hey, okay, what's n of C? And it gives me this next number there. And let's do that one more time, n of D. And notice that when I apply it, now I had a really bad guess to start with. 3.5 would have been a much better guess. So I implemented Newton's method on a better guess 1, 2, 3, 4 times. And notice the 4th time and the 3rd time, there's no difference out to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 decimal places. Holy crap. So even on the third try here, the second and third try match out to 1, 2, 3, 4, 5, 6, 7, 8 places if we round. So when Newton's method does converge, it converges pretty fast. And most calculators allow you to do this pretty quick. If you have a TI type calculator, you can use the answer feature and repeat it. So I'm just going to do this on a let's use the scientific calculator. So I would type in my first guess. So let's say that was 2.5. And then I just use the previous answer button to come up with more stuff. So I know I have a fraction. And I'm going to have the previous answer squared, and then plus 12. And then I want to divide by 2 times the previous answer. And then what I can do is I can just copy, oh, it should have been 3.5. And the cool thing is if I change my guess, it automatically changes below 2, which is nice here. Oops, I should not have hit enter. There we go. And then I can just copy this sucker right here in this calculator. On a TI type calculator, you would just keep hitting enter, and it would always look at the previous answer. So you would type this once, you enter your number, type this once on a TI type calculator using the previous answer, and then if you just hit enter, 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 it'll just keep reapplying it to the previous answer. Here I have to paste it in to make it work. And then I just keep pasting it in, and then pretty quickly I max out the number of decimal places it has to work with. So when it does work, it works really fast, which is kind of nice. Similarly, I could do this in a spreadsheet, and a spreadsheet is a pretty cool way to do it too. If you like spreadsheets. So usually I like to make some notes about what I'm doing in the spreadsheet. Come on, there we go. So I might indicate what my initial function was. F of x is x squared minus 12. And then I'm going to make just a note of my Newton's method. I'm going to call it n of x for Newton. And that was equal to parentheses x squared plus 12 divided by, and then parentheses 2x. And then to use this, you know, I could just number my guesses, guess 1, guess 2, and so on. And then over here, I'll put the result. So I have to type the first number. I don't really need equals, so 3.5. And then to get the previous answer, it's just a matter of clicking on a cell. So equals, parentheses for the numerator, the previous answer squared, plus 12, close the numerator, divide, start the denominator with parentheses, 2 times the previous answer, close parentheses. So you got to be careful with parentheses because you don't have a stacked fraction here. And then all you have to do after that is just click back on it, grab the autofill button and drag it down, and we can see it converges pretty rapidly here with the number of decimal places I have available. So that by the 5th try, I've maxed out the number of decimal places the spreadsheet's showing me. And I could get it to show more, I think, by just, let's see, how do we get it to show more? I think we have to highlight and say, show me more decimal places. So if we needed more, we can certainly get them. And you can see we maxed out by the 5th step, the number of decimal places. And then it's kind of bouncing around just because it's got rounding error that it's struggling with there. And that's going to happen sometimes. If you've ever done any computer programming, there's only so many digits that you can store in a float. So that's inevitable. Managing decimal places is a challenging computer science issue. Okay, so next, the geometric significance of Newton's method for square roots. So I'm going to pick up with this right here for Newton's method. So we started off with f of x equals x squared minus 12, and we're looking for zeros of that. We know the zeros should be plus or minus the square root of 12. And so then the question is, how is something like a square root of 12 calculated on a calculator? So they use some kind of recursive algorithm. And these days, it's usually not Newton's method. There are many other methods that converge quicker. But applying our Newton's method here, we get that the new x value is going to be equal to the previous x value squared plus 12 over 2 times the previous x value. So what I'm going to do here is I'm just going to divide top and bottom by that previous x value. When I do that, this cleans up a little bit. So x squared divided by x is just going to give me x. So there's my previous number. And then I have plus this 12 over x, all divided by 2. And the way to think about this right here, remember my first bad guess, x1 was 6. And if you consider the 12 over that, that's going to be 2. And the interesting thing about the numerator here, the numerator basically gives us two numbers, A and B, where A times B is always 12. And the significance of that is we're then averaging those two numbers. Now, we're trying to find a number A where A times A is equal to 12, right? That's what the square root says. What is A? So A times A is 12. And what Newton's method is basically doing in this case, it's saying, all right, take any number, find the number we would multiply by, right, the B, in order to get 12. If they're not the same, average them, right? If they're the same, we get the same number. If A and B are equal, then A plus A over 2 is A, right? We got the square root, we're done. Otherwise, we just keep repeating this process with a next guess. So we did this here, and that came up with a 4. Or no, I think it came up with 2 and then 4. So we got a 2, then we repeat it again, we got a 4. So let's think about the 4. Let's say my x2 was equal to 4. Then Newton's method in this version right here says take 12 divided by that number, right? So 12 divided by 4 is 3. And remember, what do 4 times 3 do? They give me 12. And so geometrically, what's happening here is we're starting off with this rectangle. Right, so 2 by 6 maybe looks like this. And then we say, okay, that wasn't a very good rectangle to get 12. We'd rather have it be a square. And then it comes up with 3 by 4. So maybe 3 by 4 looks like that right here. And then it just keeps getting better. It says, nah, 3 isn't close enough. Let's try 3.5. So then it gets 3.5 times whatever. And so Newton's method is geometrically zooming in, changing any rectangular you get, any rectangular product you guess at with a bad guess, and eventually turning it into a square, which is what we're looking for in the end, which is kind of cool. So geometry of Newton's method for squares, I think is pretty awesome. All right, so let's apply it to another problem. So we'll do an easier one and then a slightly harder one. So let's take the function f of x equals x squared minus x minus 1. I think it's the one I want. This is a polynomial right here whose roots are the golden ratio, if you've ever heard of that in a geometry class, which is kind of neat. So we want to find the zeros of this polynomial. So what are the zeros of this right here? So for Newton's method to find the zeros, we first find the derivative. So f prime of x here is going to be 2x minus 1. And then we set up Newton's method to find our new x. So our new x is always going to be our previous x, we'll just call that x1 for now, minus the function x1 squared minus x1 minus 1 over 2x1 minus 1. So the function divided by its derivative. And then it's usually worth it to clean it up. So a little bit of algebra to clean that up. We'll have to multiply top and bottom of this by our common denominator here. So 2x1 minus 1 there, multiplied by 2x1 minus 1 here. So that's going to give us 2x1 squared minus x1, right? We have to distribute there. And then we have to distribute the negative through here. Be careful with your signs. So that'll be minus x1 squared plus x1 plus 1 all over 2x1 minus 1. And then we do have some like terms here that clean up, right? So those guys clean up pretty nice. And these guys clean up pretty nice. And we have the 1 just hanging out. So we get our new x is now going to be x1 squared plus 1 over 2x1 minus 1. So this is our recursive formula that we just keep applying. Now we do need a guess at a 0 here. So somehow we have to guess at that. Now my claim is that one of the roots here is around 1.6, which is to 1 decimal place, the golden ratio. So let's use that as our first guess. So you got to have a reasonable first guess. Otherwise, you could bounce off into infinity, or you could head toward the other root or another root that this polynomial might have. And this works for more than just polynomials, by the way. It works for any function. So let's use a calculator. What do you want me to see me do a spreadsheet again, or do something like Geogebra or Desmos? Let's get a vote from the audience here. Kelsey says Desmos. I'm going to use Desmos Scientific to do it, which is more like a handheld calculator would do it. So then I make my first guess, so that would be 1.6, enter. And then I use the previous answer button to instead as my x1, right, my previous x value. So my version of Newton's method for this function was my previous answer squared, and then plus 1, divided by 2 times the previous answer, minus 1. Let me double check. I typed that right. That looks like a reasonable result there to me. Plus 1 on the top, minus 1 on the bottom. Okay. So there's, and then I just copy that. And on a handheld calculator, you would just hit enter again after you do that. So you enter, you get your number, and then keep hitting enter, and it'll keep iterating through Newton's method for you on a handheld calculator. Here I have to do Control V a couple times, and I can see I'm zooming in pretty quick. I already have like 8 decimal places there. So one more time, and I maxed out the decimal places on the calculator pretty quick. So once you have a device that will repeat a calculation, which is a handheld calculator, Desmos Scientific, a spreadsheet, Geogebra, all of those can repeat them pretty easily. You just got to start zipping through it and you're done. So the hard part is making sure you get the derivative right. And then if you need to do any algebra to clean it up, you know, don't make any mistakes in your algebra. We could have just put in the raw version of Newton's method. Nothing wrong with that. But this is just less calculations. So if I was writing a computer program to do this, I would go for this one because it would be a little bit faster than the one above, less calculations. All right, let's do another one. Now, with quadratic functions, we have a quadratic formula, and we can take square roots pretty easy. Turns out, just like there's a quadratic formula, there is a cubic formula. It's quite nasty. There's also a 4th degree formula, but it's been proven that there isn't a general formula for polynomials above 4th degree. So for a 5th degree polynomial, there's no guarantee that you can find an exact root. So I'm going to put up a 5th degree polynomial here, relatively simple one. Let's take x to the 5th power minus x cubed minus 3. And I want to find its zeros. Now with a 5th degree polynomial, you're guaranteed at least one real zero because its end behavior is either like this, could wiggle in between, or it's like that, could wiggle in between. Since this has a positive leading term, its end behavior is like this right here. So there's gonna be at least one root in there. And then the other 4 roots would be imaginary, complex. So I do need a guess here. So we're going to start by graphing this sucker. So let's go to Desmos and actually, or Geogebra, new one. So f of x is my original function. It is x raised to the 5th power minus x raised to the 3rd power minus 3. And so I can see, okay, it's got 1, 0. Now, Geogebra has some algorithm in their program to estimate that number, and so they're giving me an estimate there. So I'm going to go with 1.4 as my estimate for Newton's method. I could actually program Newton's method right into Geogebra here by just saying, hey, I know the derivative. The derivative is 5x raised to the 4th minus 3x raised to the 2nd is the derivative. And then Newton's method on that, I could call n of x, would just be whatever x value I give it minus f of x over d of x. Right? That's what Newton's method says. And so Geogebra just wrote that out for me there. And then I can just start applying that with a first guess there. And so my first guess was going to be, what, 1.4, is that what I said? Let's see, in general, we don't, the actual function we get isn't, its graph isn't all that significant because we're iterating through it. And this graph does not show an iterative process. That's a whole different idea, computer science wise and graphic wise. So if I focus on this guy right here, yeah, 1.4 is going to be my first guess. So 1.4, and then I just repeat that. What is n of A, my first guess? What is n of B, my second guess? And so on. And I have, after, now this one is wicked steep, so it's not zooming in as fast as the quadratic. Notice that I only have 2 decimal places so far after 2 times through it. So now I have 4 decimal places after 3 times through it. So you have to keep running through Newton's method until you see some decimal places starting to get fixed. So after one try, right, I had 1 decimal place. 2 tries, I got 2 decimal places. After the 3rd try, I've got 4 decimal places. And the 5th try, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 decimal places. Oh my gosh, right? We went from 1 to 2 to 4 to 10 decimal places with Newton's method. So again, when it does converge, it converges pretty fast. So it's fairly efficient, but people have come up with some more clever ways to go about estimating these kinds of values right there. And again, there is not a exact value of this that we have a technique to find that exists at the moment. Will there be? There's no general formula for finding 5th roots, but that doesn't mean this one might have some clever trick somebody could figure out to find an exact value. So that's a whole nother story, and people do study that kind of stuff regularly. They get PhDs and stuff like that. Okay, so I think we are ready for Kelsey's question. So again, with a computer system like this, you can pretty quickly build Newton's method and then start iterating through it. And again, I could have also done that in a spreadsheet, pretty straightforward. So maybe use a spreadsheet for one of these other ones. All right, so into the homework questions. And I know some of you guys are computer science students, and so I thought that seeing a use of calculus toward computer science would be an important thing. So I remember when, like in the early days, like the TI-81 before the TI-82, you could do a little programming on it. So I could program it to do Newton's method and get roots that the calculator couldn't find on its own, which I thought was pretty awesome way back then. So let's see, resume homework, and question number 6. Take a peek. So here, we're going to use Newton's method to approximate a root to the equation. And this is a really cool one to look at because we can use logarithms to solve for exponents, and we have other techniques for solving linear equations, but it turns out there isn't an algebraic technique that can solve these two when you put them together. So the only way to solve an equation like this is some kind of approximation method. So we really are forced to use something like Newton's method. All right, so screenshot you, write up the results. So we just want a couple, and they're giving us a first approximation here. They're saying, hey, try 1 to start with. And when I took calculus, it was before graphing calculators, and if the instructor said, here's the equation, come up with a first guess, that was like the hardest part. It's like, oh man, where do I start? I don't have a graphing calculator to do this for me. So in order to use Newton's method, we need first a function that we can set equal to 0. So we have to clean up that equation so we can do so. So we would subtract the 6, add the x over. So our f of x in this case would be e to the 0.1 x squared minus 6 plus x. So that's the function we start with, because Newton's method needs something that you can set equal to 0. Once we have that, it's pretty straightforward. We take the derivative, f prime of x. So let's see, chain rule for this sucker right here, the derivative of e to the something is e to the something. Chain rule says then multiply by that inner derivative. So the inner derivative is the derivative of 1/10 x squared. So that would be 2 times 1/10, or 2/10 x. So that's the derivative of the exponent, times e to the 0.1 x squared. Derivative of -6 is 0, derivative of x is 1. So that is the derivative function there. And then for Newton's method here, my new x values, and often instead of writing a new x, they'll do something like xn equals, and then on the other side, we put an xn minus 1. And I always found that kind of bulky. It's technically the way we're supposed to do it, but just writing a little x1 is neater. But this is the preferred notation. So then we have our original function, which is now this sucker up there. So e to the 0.1 x squared minus 6 plus x over 0.2 x e to the 0.1 x squared plus 1. And so again, the technical way to write it using the proper notation, let's slide that down a little, would be xn is the current, whatever n is, 2, 3, 4, n minus 1 means the previous x value. So you will see this often when you look up Newton's method. So that would be e to the 0.1 x sub n minus 1 squared minus 6 plus x sub n minus 1 all over 0.2 x sub n minus 1. See what I mean about slightly more tedious to write it out. E to the 0.1 x n minus 1 squared and plus 1. All right, and that's an x1, that's an x1. And so now it's just a matter, I don't think this cleans up much algebraically, but I guess we could do it for fun. We would have to multiply top and bottom here, and that's not gonna get any better. I'm going to write it down anyway just to see. So multiplying these guys together, I would get 0.2 x1 squared e to the 0.1 x1 squared, and then times 1 times x1, and then minus each of these guys, we get to distribute. So that would be minus e to the 0.1 x1 squared plus 6 minus x1, all over 0.2 x1 e to the 0.1 x1 squared plus 1. And the only thing I can combine in the top are the x1s there. So 0.2 x1 squared e to the 0.1 x1 squared minus 2 x1s. We still have that e to the 0.1 x1 squared hanging out and the plus 6. So it doesn't really clean up very much. I don't know if this red uses much less ink. I think it actually might use slightly more. I have to weigh them, do that later. Yeah, so either we have the green way to write it down in a calculator, or we have the red way to write it down. Oops. And your pick as to which one you think is the better version. I'm going to go for the first way here and pick your calculating device. So here we're just asked to do 2 iterations through. And again, on a handheld calculator or any of these others, that's pretty easy to do once you type it in once, but you got to get that in right. So let's hope I can remember all of that in my head. All right, so let's see, what do I want to do this time? I think I'm going to go for Geogebra for this one here. No, I don't want save anything. And so I'm just going to go straight to my guess. They said guess at 1 to start with. And yeah, then I have to enter it as a function, unfortunately, of x. So it might be slightly less work to enter this on something like scientific calculator. So I have x minus fraction, and my original function was e raised to the 0.1 x squared minus 6 plus x. Oops, wrong spot. You type it right. And then divided by the derivative, which was 0.2x e raised to the 0.1 x squared, and then plus 1. Make sure I type that right. Yep, looks right. And then it's just a matter of cycling through it. So n of my first guess, A. So that would be my x2, n of my second guess, B. And so there's my next one. So they only wanted 2 of them. But again, once you get it set up, you can get as many as you want pretty darn easy on the right calculating device. You just have to decide what calculating device do you like to use. Questions on this one? Okay, let's try another one. And so if you do start calculating these and something went wrong, then it's most likely there's a slight error in the way you typed this into your calculator here. Number 7 was asked about. Same thing on this one. So this is, again, one of those situations. We have a natural log and an arctangent. Either one is a bit of work on their own to find roots, but together, it's likely impossible to find an exact value. So we're forced to do an approximation. And so it turns out the majority of mathematics that happens in real life is all computer program approximations. And so then the question is, how do we make those approximations? So this is one technique for that. And actually, I do program, but I only got into programming to solve math problems. My degree is in math, not computer science. But I got into computer science just because of mathematics, because I realized, oh my gosh, most things don't have a solution. I got to program a solution, or somebody does. And computers have really changed mathematics dramatically, opened up whole new areas of mathematics that didn't exist before computer stuff. All right, so this one we have to rewrite it so it's equal to 0. And so I'm going to choose to subtract the arctangent over. So then my function in this case would be the natural log of 4x minus the arctangent of x minus 0.2. And then the big question here is, can we remember that derivative off the top of our heads? So let's see, my recollection is that the derivative with respect to x of the arctan of x is 1 over x squared plus 1. That up to double check. Anyone want to correct me on that if I messed it up? So let's see, where am I going to go to get that? How about we just search for derivative formulas, or even better, use the derivative calculator. X. Okay, yep, so I was right. 1 over x squared plus 1 is the derivative. So now we just have to apply the chain rule to that. So derivative of the natural log is 1 over whatever's inside. So again, this is a function within a function, so I'm going to get a 1 over 4x. And then, since that's not just an x, I have to multiply by 4x, the derivative of 4x, which is 4. Minus the derivative of the arctangent is 1 over whatever's inside squared. So that would be x minus 0.2 squared plus 1 times the derivative of whatever's inside. Well, the derivative of x is 1, the derivative of 0.02 is 0, 1 minus 0 is 1. So I just have a 1 in there, so that's not too bad. Cleaning that sucker up a little bit, we have a derivative of 1 over x minus 1 over x minus 0.2 squared plus 1 is the derivative function. And could we subtract those and rewrite it? Yeah, but I don't think it's going to get any better ink-wise. So I'm just going to leave that the way it is. So then our new x, based on a given x, is going to be x1 minus the original function, natural log of 4x1 minus the arctan of x1 minus 0.2 all over 1 over x. Oh, not all over. That was too much. Chill, Gary. Whoa. Just the function is divided by the derivative, not the x in front. 1 over x1 minus 1 over x1 minus 0.2 squared, then plus 1. And again, we could apply some algebra to the denominator to try and clean it up, flip it, but I don't think it'll use much less ink overall. It'll probably be pretty close to the same, maybe a touch more. So I leave it up to you to try to see if you can use less ink on that in the future. And then it's time to go to a calculator and start plugging in. So they're saying your initial x1 should be 0.1, and they want, what, a couple more here? They want the 4th and the 5th. Okay, so pay attention to that. So then it's a matter of picking your calculating tool. And which one do I want to do? I think I'm going to go with Geogebra again. So let's just delete a few things here. And we can just clean this sucker up. All right, so fraction. So again, the hard part is getting it set up. Once you have it set up, it's pretty straightforward. So natural log of 4x minus the arctan of x minus 0.2 divided by 1 over x minus 1 over x minus 0.2 squared plus 1. Did I type it correctly? I think that looks right. Minus, yep, looks good. Set the first guess. And then start going. So they wanted the 4th and the 5th, so that's my first one. They labeled that x sub 1. So plug in my a, so there's my x sub 2, x sub 3, x sub 4, and x sub 5. So you just got to count carefully and keep track. So they want me to plug in those two numbers here to a certain amount of accuracy. And it looks like after the 5th try, I have two decimal places of accuracy. I'm kind of curious on a 3rd try here. And again, the graph of this function is irrelevant. So Newton's method graphically is not used like a graph we normally do. We're using it as an iterative function instead, which is a whole nother way of using a graph. Yeah, so after the 6th time through, I finally get 4 decimal places, 5, almost 6 decimal places locked in there. Okay, so it's a little slow at first, but all of a sudden, wham, it says, I got it. If you're getting an undefined answer, then that means you have an error in something you plugged in. So either you typed the first guess wrong or you typed your Newton's method wrong on your calculator. So again, this is definitely undefined for some numbers. So if I tried to plug in 0.2 here, I would get undefined. If I tried to plug 0 here, I'd be undefined. So there's certain numbers that definitely will be. So I'd have to see your numbers to figure out what went wrong. But usually undefined is a bad guess or a typo when you use Newton's method. All right, let's try another one. Number 9. Okay, so here we have the graph of the function and we want to estimate the root to 5 decimal places. So like before when I was using Newton's method, I'm more concerned not with how many tries it takes, but looking at the decimal values as I progress through Newton's method and when do those decimal values start to get locked into place. And so here I can see that I have a match on the 6th try of 1, 2, 3, 4, 5, almost 6. There's a little rounding error on the 6th one here, but for sure I have 5 decimal places locked in. The question is the next one a 4 or a 5? And I would have to, like if I needed 6 decimal places, I would have to go one more try on this one. And of F, and then here, okay, so it was a 4, 9. So I now have like 10 decimal places locked in on the 6th try. Yeah, so usually if you're close to what you want on one try, if you do one more try, you get way more than you thought you needed. So again, Newton's method, when it does go, it goes pretty good. So on this one right here, similar to the last ones, we have to get everything on one side of the equation, and then we just have to run through Newton's method until we see 5 decimal places locked in or more, and then we can report back and say, aha, this is what I think the root is. And here you can see I've got an estimate of it. I show the 2 functions. So I can say, well, a good guess might be like 5.7 on this one is what I would guess at as my starting value, and then see what happens. So I'm going to leave that for you to try. It's pretty similar to the one we just did. All right, we're almost at the end of fun time with math today. So keep working on those problems there. If you get stuck, you always have that, where the heck's the message me button? What? Huh, that's weird. I usually have that everywhere. I'm gonna make sure it's in there. If you get stuck, message me. That would be here and there. Okay, now we got a message me button there. Okay, so message me if you get stuck on any of these. If you do get stuck, send me a picture of also of what you tried, maybe a screenshot or something like that, so I can help you out to figure out, like if you get an undefined value, I can help figure out why, but I gotta see it, how to figure that out. So one more big topic, just pointed out before we depart from each other, is the idea of an antiderivative, which we'll take a look at tomorrow. So that's the last topic, and that leads us into Calc 2. So a quick note on antiderivatives. An antiderivative and an integral are related, but they're not exactly the same thing, but we use one to get the other. So a derivative is like division, and an antiderivative is like a multiplication, and that's related to an integral. So where's my whiteboard? Oh, it's over here. So for example, we know, I'll just do this one example and then shut up. We know that the derivative with respect to x of the sine of x is equal to the cosine of x. So vice versa, the antiderivative of the cosine of x is the sine of x. And we use these ideas of antiderivatives to generate what are called integrals, and integrals are used to solve the area problem in calculus that we talked about way in the beginning of class. So we'll take a peek at that tomorrow. Pretty straightforward topic. And then we are done. So have a good day. I'll see you tomorrow. Adios.